then we have an underdetermined system which has infinite solutions. So this is not interesting if you want to recover highly structured signals, but what compressed sensing does is it imposes structure on X. So now I'm going to talk about some different kinds of structure that have been proposed in prior works and how it relates to the current work. So the classic structure that's imposed on these signals is that these signals are assumed to be sparse when viewed in a basis P. And this is true for many real-world signals. For instance, images are known to be sparse in the wavelet basis. Audio signals are sparse in the Fourier basis. And then once we have this kind of assumption and we're trying to do compressed sensing, then we get very good celebrated results in compressed sensing, which say that if we choose a measurement matrix to satisfy certain eigenvalue conditions, any signal which is L-sparse, by which I mean it has no more than L non-zero entries, can be recovered with measurements which are L log n. So L is the sparsity level, and n is the dimensionality of the data, and these results hold with high probability. So in practice, for acquisition, our matrices are simply random Gaussian and Bernoulli matrices. So we are just doing random projections of our signals, and we're trying to recover them by solving an L1 minimization problem, which can be done efficiently using methods such as lasso. So this works really well. But in recent work, Bora and others at last ICML showed that instead of relying on assumptions such as sparsity, we can impose structure based on a generative model. In particular, they said that the signals that we really care about would lie on the range of a latent variable model. So here is how a latent variable model simply looks like. You have a latent variable z, which is usually much lower dimensional than x, and you sample z from some prior distribution. It could be an isotropic Gaussian, and you pass it through a mapping which generates x. So here, what I'm calling G on the slide is a deterministic mapping from z to x, which is true when you have a GANs. In the case of VAs, you have a probabilistic mapping, so G here would correspond to the mean function that maps Z to a distribution over X. Okay, so with generative model-based recovery as well, we can get some really nice guarantees. And the guarantees look of the form that if we choose A in a certain way to satisfy some eigenvalue conditions, then any signal X that lies on the range of a generator that's L Lipschitz can be recovered with measurements which are of the order of K log LR. So R here is the radius which upper bounds the prior signal Z. L is the Lipschitz constant for the generator, and K is the dimensionality for Z. So again, these results hold true with high probability. In practice, what we do is we select random Gaussian or Bernoulli matrices for acquisition, that's our A, and for recovery, we solve an L2 minimization problem just using SGD. The minimization objective is that we want the measurements Y to not differ too much from a signal that lies on the range of the generative model when it's transformed through this matrix A. So we are searching for the Z such that this objective is minimized. But there's a problem with this issue, with this method. And the problem is that Z here is really low dimensional in comparison to X. So the signals that we recover are restricted to a range that does not span the full Rn space, the full real value space over n dimensions. So the recovered signals can only correspond to the signals that are appropriate for the range of the generative model. So this is the head-to-head comparison between two different kinds of structure that I've talked about so far. The first kind of structure is based on sparsity, where we are saying that we'll use lasso to recover our signals, and this is domain agnostic, which on the other hand, a latent variable generative model enjoys the fact that it can impose stronger priors because it's learned for a particular domain. However, what the generative model suffers from is that a fact that it can only recover signals that are on the range of the generative model, which is not the full space of signals we care about. As a result, in practice, we see that even as we increase the number of measurements M to go up to the dimensionality of the signal N, the recovery error for a latent variable generative model does not saturates to a non-zero value and does not vanish. Okay, so in this work, we propose a new kind of structure which allows us to impose strong priors based on generative models, but as well as deviate in sparse ways from the range. So in particular, the signals that we are being recovering will have this form of g of z plus a vector nu. So g of z is going to correspond to a signal that lies on the range of the generative model, and nu here is going to be another vector which, when viewed in a basis B, is sparse. So pictorially, if you want to compare it with what I've talked about earlier, so here's an illustration. So here I'm showing the structural prior imposed in the gray shaded regions. For simplicity, here both x and y are one-dimensional, so our linear system is simply a line that's in black, and red here denotes the signal that we are recovering. So in the case of lasso, we look for a signal that's sparse, so it recovers the red point that you see out there. If you have a generative model, you impose a stronger structural prior that's more sensitive to the domain being sensed. However, the signal that's recovered is constrained to lie on its range. So it may not even satisfy the linear system of equations. In the structure that we are imposing, we again have a prior that's based on a generative model, but we allow sparse deviations. So it's able to recover signals that lie, that satisfy the constraints specified by the linear system of equations. Okay, so how would this work in practice? For acquisition, we can again rely on random Gaussian or Bernoulli matrices, which have very nice properties, and recovery would be done again through L2 minimization and an SGD-based method, but the optimization problem looks different from before. Now we're trying to recover, again, some sparse vector nu when viewed in the basis B, such that the observed measurements y is equal to a times the signal which allows for sparse deviation from a generative model. So z here would be some vector that's sampled from the prior of a generative model. G of z gives us a signal on the range of the generative model, and we allow it to deviate in sparse ways by adding this another vector nu. So in this case, we're optimizing over both the z, the vector from our prior, as well as nu, which is the sparse vector when viewed in the basis B. Okay, can we say something about it theoretically? And it turns out we can. So again, we can say that if we have a measurement matrix A satisfying eigenvalue conditions, such as a random Gaussian matrices, and a generator that Lipschitz, then there exists some recovery procedure that can recover L-sparse signals in measurements that are logarithmic in the Lipschitz constant of the generator times the dimensionality of the latent space K, and an additive factor of the sparsity level L times logarithmic in the dimensionality of our signals, that's n. As usual, these results hold true with high probability. And in our paper, we talk about even better results for the specific case when the generative function G is specified as a deep neural network with only ReLU activations. Okay, so here's the story so far. So we proposed a new kind of structural prior on the signals that we care about for compressed sensing. Unlike lasso-based recovery, our framework imposes a very strong generative prior on the signals that we care about. However, unlike the generative model-based methods, our signals are not constrained to lie on the range of the generative function G, and they can span the full real value space over n dimensions. Okay, so we did some experiments on the two benchmark data sets of MNIST and OmniGlot, and we varied the number of measurements from 50 to all the way up to 750. Our evaluation metric was the L2 error in recovery of the test signals. For the generative model-based methods, we used variation autoencoders. Our acquisition was done through random Gaussian matrices, and we compared 3 different recovery procedures: lasso, a generative model that's VAE, and the sparse VAE method that we propose. So here are what the results look like. So on the x-axis, you see the number of measurements being varied from 50 to all the way up to 750. On the y-axis, you see the L2 error averaged over the pixels. So we see that the lasso-based methods, because they do not have a strong prior over the domain being sensed, they incur a very high loss when the number of measurements are small, but this loss vanishes as we increase the number of measurements, as expected. On the other hand, the VA-based methods, when the number of measurements are small, they start off really well. The L2 error is really low. However, they quickly saturate, and this error does not vanish as we increase the number of measurements. Our proposed framework, Sparse VE, borrows the best of both worlds, and it starts off with a low error even when the number of measurements are low, and this error continues to vanish as we increase the number of measurements. Okay, so one question we can ask is, if our goal was really to acquire high-dimensional signals efficiently, it's not always the case that we might have a pre-trained generative model to impose this strong prior. So in order to get past this difficulty for some domains, we tried this experiment of transfer compressed sensing, where we train our generative model on some source domain, which is similar to a target domain, but not the same. But the key property of the source domain is that we have access to large amounts of training data, whereas for the target domain, we assume we don't have any training data for our generative model. So because we assume this setting, and we are experimenting with omniglot and MNIST, then we see this trend where we choose our source to be omniglot, try to transfer it to MNIST, and vice versa as well. Then these plots show that the lasso error does not change because it's not really learning the structure, but VE severely underperforms. Even the sparse VE method that we propose underperforms a bit. However, it is still better than the lasso-based methods for both the regimes of low measurements and high measurements. Qualitatively as well, we see these kinds of results where on the top row I'm showing the original signals that we are trying to sense, and then the next 3 rows are the methods we're comparing against. And we see that in many cases, lasso fails in capturing the right structure of the domain we care about, whereas a VE that has been trained on MNIST and cannot escape the range of generative model that's expressed by MNIST continues to return signals that look like MNIST digits. On the other hand, our method tries to recover signals which look much more like omniglot. So as a summary, the takeaway from this work is that sparsity assumptions can coexist and aid generative model-based methods for the purpose of compressed sensing. Our code for reproducing those results is open source. And for more questions, I would encourage you to please come and visit our poster. Thank you.
Thank you. Questions?
Can you repeat the questions? Measurements that are? Can you use a mic, or can you say it louder? I see. OK. I got your question. So the question is, how do we deal with measurements which are noisy? And for the purpose of this talk, I was using the linear system of equations, which is saying y equals ax. But in the real world, there's noise. And this was only for the purpose of this talk. In our paper, we explicitly handle the case where there is noise in our measurements. So we assume a Gaussian measurement noise model. So we model the noise in our observed measurements as Gaussian. And even in those cases, these theoretical guarantees do carry over. Thanks.
Thanks very much.